For billion miles from Earth, in the frozen darkness at the edge of our solar system, NASA's James Webb Space Telescope has detected something that shouldn't exist. On Charon, Pluto's enigmatic moon, molecules of carbon dioxide and hydrogen peroxide rest on ancient ice. These aren't just chemicals, they're evidence. Evidence that challenges everything we thought we knew about how worlds form in the outer reaches of our cosmic neighborhood. What Webb found in October 2024 is rewriting the story of planetary formation, and the implications reach far beyond one distant moon. This is the story of that discovery and of the 4.5 billion-year journey that led us here. To understand what makes this discovery so profound, we need to understand how we detect chemicals on a world nearly 4 billion miles away. The James Webb Space Telescope doesn't take pictures the way we typically think of photography. Instead, it analyzes light specifically, infrared light, the kind of radiation we experience as heat. When sunlight strikes Charon's frozen surface, some of that light bounces back into space. But not all wavelengths bounce back equally. Different molecules absorb different wavelengths of infrared light. Carbon dioxide, for instance, absorbs light at very specific frequencies, a unique fingerprint that no other molecule shares. The same is true for hydrogen peroxide, water ice, and ammonia. By measuring exactly which wavelengths of light are missing from Charon's reflected glow, Webb can identify which chemicals exist on its surface. It's spectroscopy, one of the most powerful tools in modern astronomy. And in late 2024, it revealed something unexpected. The spectroscopic data showed absorption features at 4.7 micrometers, the signature of carbon dioxide. Additional features appeared at wavelengths corresponding to hydrogen peroxide. Both compounds were detected alongside water ice and traces of ammonia. Scientists expected water ice. Charon is, after all, an icy moon in the frozen outer solar system, but carbon dioxide. That suggested something more complex, something dynamic. And hydrogen peroxide, a compound that forms when radiation bombards ice, indicated that chemistry is still happening on Charon's surface today, even billions of years after its formation. But to truly appreciate why this matters, we need to go back. Back to 1978, back to the moment we first discovered Charon existed at all. June 22, 1978, the United States Naval Observatory in Flagstaff, Arizona. Astronomer James Christie was examining photographic plates of Pluto, trying to refine measurements of the dwarf planet's orbit. But something was wrong. The images were blurry, elongated in a way that suggested a flaw in the telescope or the photographic process. Except the stars in the same images were perfectly sharp. Christie examined plates taken on different nights. The elongation appeared consistently, but it changed orientation. Sometimes it pointed one direction, sometimes another. And then Christie realized what he was seeing. Pluto wasn't alone. Something was orbiting it, something large enough to create a visible bulge in the photographic emulsion. He had discovered a moon, Charon. The name came from Greek mythology, the ferryman who carried souls across the river Styx to the underworld. It was appropriate for Pluto's companion. But Christie also chose it for another reason. It contained the first four letters of his wife's name, Charlene. As observations improved, astronomers realized Charon was extraordinary. At roughly 1,212 kilometers in diameter, it was about half the size of Pluto itself. No other moon in the solar system was proportionally so large relative to its parent body. Our own moon is about 1/4 Earth's diameter, impressive, but nothing like Charon's ratio. This massive size meant that Pluto and Charon don't orbit the way typical planets and moons do. Instead of Charon circling Pluto, they both orbit a common center of gravity, a point in space between them called the barycenter. They're locked in a gravitational dance, spinning around each other like two figure skaters holding hands. And there's something else. Both worlds are tidally locked, not just Charon to Pluto, but Pluto to Charon as well. They eternally show the same face to each other. If you stood on Pluto's surface, Charon would hang motionless in your sky, never rising, never setting. The same would be true from Charon. Pluto would remain frozen at a fixed point above the horizon. This mutual tidal locking is unique in our solar system. It suggests an intimate gravitational relationship, one that's had billions of years to reach this equilibrium. But how did they form? How did these two worlds come to orbit each other in such perfect synchronization? For decades, we could only speculate. Charon remained a mystery, a fuzzy dot in even our most powerful telescopes. We knew its size, its orbit, and little else. Then came New Horizons, and everything changed. But before we explore what New Horizons revealed, let's take a moment. If you're fascinated by the mysteries of the outer solar system, if you want to join us as we explore the latest discoveries in planetary science, consider subscribing. We're building a community of people who believe that real science is more incredible than any fiction, and there's so much more to discover. Now, let's continue our journey to Charon. To understand why Charon's composition matters, we first need to understand what makes Charon so unusual in the first place. Let's start with that binary orbit. When we say Pluto and Charon orbit each other, we mean that literally. The center of their mutual orbit, the barycenter, lies in the space between them, about 960 kilometers above Pluto's surface. This is fundamentally different from, say, Earth and the Moon, where the barycenter lies inside Earth itself. This binary nature raises a critical question. Are Pluto and Charon a double dwarf planet system, or is Charon simply an unusually large moon? The International Astronomical Union hasn't settled this definitively, but many planetary scientists consider them a binary system. The orbital period is 6 for Earth days. That's how long it takes Charon to complete one orbit around the barycenter, and it's also how long it takes Pluto to rotate once on its axis. This synchronization isn't coincidence. It's the result of tidal forces acting over billions of years. Tidal locking occurs because of the way gravity works across distance. The side of Charon facing Pluto experiences slightly stronger gravity than the far side. This gravitational gradient, this tidal force, creates a subtle bulge. Over time, friction from this bulge dissipates rotational energy, slowing Charon's spin until one side permanently faces Pluto. The same process worked in reverse, with Charon's gravity locking Pluto's rotation to match the orbital period. The result: a stable, mutually locked system that could persist for billions of years. Now let's talk about size comparisons, because Charon's proportions are truly remarkable. Charon's diameter is 1,212 kilometers. Pluto's is 2,377 kilometers. That makes Charon 51% the size of Pluto, roughly half its diameter. Compare that to other moons in our solar system. Jupiter's Ganymede, the largest moon anywhere, is only 7.8% the size of Jupiter. Saturn's Titan is 9.2% of Saturn's size. Even our moon, which formed through a giant impact and is unusually large for a satellite, is only 27% of Earth's diameter. Charon stands alone in this regard. Its massive size relative to Pluto is one of the key clues to understanding how it formed, a mystery we'll explore in depth later. When New Horizons sent back the first detailed images of Charon in 2015, scientists saw a world far more complex than anticipated. The northern hemisphere was covered by a dark, reddish region informally named Mordor Macula, after the shadowy land in Tolkien's fiction. This reddish material puzzled scientists. Was it organic compounds? Radiation, processed ice, something else? The southern hemisphere looked entirely different. Smooth plains stretched across vast regions, interrupted by scattered impact craters and enormous chasms. Some of these canyons extended hundreds of kilometers and reached depths of 7 to 9 kilometers, comparable to Earth's Grand Canyon. What could have created such features? One possibility: a subsurface ocean that once existed inside Charon. As this ocean froze and expanded, it could have fractured the surface from within, creating the canyon systems we see today. But we're getting ahead of ourselves. Let's talk about the mission that gave us these revelations. January 19, 2006, Cape Canaveral, Florida. An Atlas V rocket lifted off, carrying the New Horizons spacecraft on the fastest journey ever undertaken by a human-made object. Its destination, Pluto and its moons, nearly 5 billion kilometers away. The mission was ambitious. No spacecraft had ever visited Pluto. In fact, when New Horizons launched, Pluto was still classified as the 9th planet. By the time it arrived, Pluto had been reclassified as a dwarf planet, a change that sparked public debate but didn't diminish the scientific importance of the mission. The journey took 9.5 years. New Horizons traveled at speeds exceeding 58,000 kilometers per hour, making it the fastest spacecraft ever launched. Even at that velocity, it took nearly a decade to reach the Pluto system. On July 14, 2015, New Horizons made its closest approach, passing just 12,500 kilometers above Pluto's surface and 28,800 kilometers from Charon. It was a flyby mission, not an orbiter. New Horizons had one shot to gather data, then it would continue past Pluto into the Kuiper Belt, never to return. Every observation had to be carefully planned and executed. The spacecraft carried 7 scientific instruments, including high-resolution cameras, spectrometers, and particle detectors. As it swept past the Pluto system, it captured images, measured surface composition, analyzed the thin atmosphere, and studied the interaction between Pluto and the solar wind. For Charon, the results were stunning. The high-resolution images revealed a world with a fractured, buried surface. The dark red polar cap Mordor macula covered much of the northern hemisphere. Scientists now believe this material originated from Pluto itself. Methane escaping from Pluto's atmosphere can be gravitationally captured at Charon's cold poles. Over time, ultraviolet radiation from the sun breaks down these methane molecules, creating complex organic compounds called tholins, reddish-brown substances that give Mordor macula its distinctive color. The smooth plains were equally surprising. Named Vulcanplanum, these regions showed relatively few impact craters, suggesting they were geologically young, perhaps less than 4 billion years old. This implied that Charon had been geologically active relatively recently in its history, resurfacing portions of its crust. Then there were the canyons. The Serenity Chasma system stretched over 1,800 kilometers longer than the entire Grand Canyon on Earth. These weren't impact features. They were tectonic fractures created by internal processes. The best explanation, Charon once had a subsurface ocean. As this ocean gradually froze, water ice. Expanded water is one of the rare substances that expands when it freezes. This expansion would have created enormous internal pressure, fracturing the surface and creating the canyon systems we observe today. But New Horizons had limitations. It was a flyby mission, and its instruments, while sophisticated, couldn't analyze Charon's surface composition in the detail needed to answer deeper questions. The spectrometers on board detected water ice, as expected, but they lacked the sensitivity to identify trace compounds or more complex chemistry. Questions remained. What else was on Charon's surface? What could the surface composition tell us about Charon's interior? About its formation? About its history? To answer those questions, we needed more powerful tools. We needed to look deeper. In the years following New Horizons' flyby, scientists developed theories about Charon's composition based on the available data and our understanding of icy moon chemistry. They expected water ice to dominate the surface, that much was certain. But they also hypothesized that ammonia might be present. Ammonia acts as an antifreeze, lowering the freezing point of water. If Charon once had a subsurface ocean, ammonia could have kept that ocean liquid longer, potentially extending the period of geological activity. Some models predicted the presence of methane or nitrogen compounds, possibly transferred from Pluto's atmosphere or present from Charon's formation. And there was always the possibility of silicate minerals, rocky material that might have been exposed through impacts or geological processes. What scientists didn't expect what seemed unlikely given Charon's distance from the Sun and its cold, inactive state was evidence of complex carbon chemistry. Carbon dioxide, in particular, would be surprising. CO typically requires specific formation conditions or delivery mechanisms. Finding it on Charon would suggest processes that weren't part of the standard model. The subsurface ocean debate also continued. Did Charon have an ocean? If so, when did it exist? And critically, could any liquid water remain today? Thermal models suggested that Charon's interior would have been warm enough early in its history to support liquid water, especially if radioactive decay and tidal heating provided energy. But over billions of years, that heat would have dissipated. The ocean, if it existed, should have frozen solid. Unless, of course, ammonia was present in sufficient quantities. Ammonia-water mixtures can remain liquid at much lower temperatures than pure water. Some models suggested that pockets of ammonia-rich liquid could persist deep within Charon even today. These were the questions scientists were grappling with in the years after New Horizons. They had tantalizing clues, surface features suggesting past geological activity, a mysterious red polar cap, evidence of internal differentiation. But they needed more data. They needed the James Webb Space Telescope. And in 2024, Webb finally turned its gaze toward Charon. The discovery that followed would exceed expectations. The James Webb Space Telescope is the most powerful observatory ever deployed in space. Positioned at the second Lagrange point, a gravitationally stable location 1.5 million kilometers from Earth, Webb's 6.5-meter primary mirror collects infrared light from across the universe. For planetary science, Webb's infrared capabilities are transformative. Unlike visible light, which can be reflected or absorbed by atmospheric haze and surface features, infrared light reveals chemical composition directly. Different molecules absorb infrared light at characteristic wavelengths, creating unique spectral fingerprints. In late 2024, a team of astronomers led by researchers at the Southwest Research Institute pointed Webb's near-infrared spectrograph at Charon. The observations were part of a broader program to study icy bodies in the outer solar system, comparing their surface chemistry and understanding the diversity of these distant worlds. The spectrograph collected light reflected from Charon's surface across a range of wavelengths from 0.7 to 5.2 micrometers. This range is ideal for detecting molecules commonly found on icy bodies, water ice, carbon dioxide, methane, ammonia, and various organic compounds. The data required careful analysis. Spectroscopic observations are rarely straightforward. Background noise, instrumental artifacts, and overlapping absorption features can obscure the signal. Researchers use sophisticated software to extract the true spectrum, comparing it against laboratory measurements of known compounds. When the analysis was complete, the results were unambiguous. Absorption features at 4.7 micrometers indicated carbon dioxide CO. Additional features in the ultraviolet and near-infrared spectrum matched hydrogen peroxide HCO. Both compounds were present alongside water ice, crystalline in structure, and ammonia hydrates. This wasn't what models had predicted. This was new. Carbon dioxide on Charon's surface is significant for several reasons. First, CO isn't stable on surfaces exposed to space weathering for long periods. Ultraviolet radiation and solar wind particles break down CO molecules over time. The fact that Webb detected it means one of two things: either CO is being continuously replenished through some ongoing process, or it's relatively fresh, recently exposed to the surface. The most likely explanation is impact exposure. When asteroids or comets strike Charon's surface, they excavate material from beneath the ice, bringing subsurface material into view. If CO exists within Charon's interior, impacts would expose it. But why would CO exist inside Charon at all? Carbon dioxide forms under specific conditions. It requires carbon, oxygen, and either heat or chemical reactions that can bind them together. On Earth, CO is produced by volcanic activity, organic decay, and combustion. Obviously, none of those processes are occurring on Charon today. The presence of CO suggests that Charon underwent differentiation, a process where a planetary body's interior separates into layers based on density. Heavier materials sink toward the core, while lighter materials rise toward the surface. Differentiation requires heat. Specifically, it requires enough heat to allow materials to flow and separate. For Charon, this heat could have come from two sources: the energy released during its formation and radioactive decay of elements like potassium, thorium, and uranium within its rocky core. If Charon differentiated, its interior would have developed a rocky core surrounded by a mantle of water ice mixed with other volatile compounds, ammonia, methane, and yes, carbon dioxide. Over time, impacts would have excavated this CO-rich material, exposing it at the surface. This supports one formation theory over another, a point we'll explore in detail shortly. For now, what matters is this: the detection of CO tells us that Charon isn't just a frozen ball of ice. It has or had internal structure. It was warm enough at some point in its history to allow chemical differentiation. That changes our understanding of its thermal evolution and, by extension, its formation. Hydrogen peroxide HEO is a different kind of clue. Unlike carbon dioxide, hydrogen peroxide doesn't require heat or internal processes to form. It's a product of surface chemistry. Specifically, it forms when high-energy radiation strikes water ice. Here's how it works. Water ice on Charon's surface is constantly bombarded by ultraviolet light from the sun and charged particles from the solar wind. This radiation has enough energy to break the bonds holding water molecules together. When a water molecule HEO is broken apart, it creates reactive fragments, hydrogen atoms, and hydroxyl radicals. These fragments can recombine in different ways. Sometimes they recombine into water, but sometimes to hydroxyl radicals bind together, forming hydrogen peroxide, HEO. The detection of hydrogen peroxide on Charon tells us that this process is ongoing. Right now, today, Charon's surface is being chemically altered by space weathering. It's not a dead world. It's an active laboratory where radiation-driven chemistry continuously transforms ice into new compounds. This is consistent with observations of other icy moons. Europa, Enceladus, and several of Saturn's moons also show hydrogen peroxide signatures. It's a common feature of radiation-exposed ice in the outer solar system, but there's more to the story. The distribution of hydrogen peroxide on Charon's surface isn't uniform. It appears to be concentrated in certain regions, particularly on the more heavily cratered, older terrain. This suggests that surface age and exposure time affect HEO concentrations. Older surfaces have been exposed to radiation longer, allowing more hydrogen peroxide to accumulate. Interestingly, the reddish polar cap Mordor macula shows different spectral characteristics. The tholins in this region appear to mask or alter the HO signature. This supports the theory that Mordor macula is composed of organic material processed from methane captured from Pluto's atmosphere. Taken together, the carbon dioxide and hydrogen peroxide discoveries paint a picture of a world with both ancient internal chemistry and ongoing surface processes. Charon isn't inert. It's dynamic, evolving, shaped by forces both internal and external. And these discoveries give us the tools we need to address one of the most fundamental questions about Charon: how did it form? There are two leading theories for how Charon came to orbit Pluto. The first, and currently favored by many scientists, is the giant impact hypothesis. This theory proposes that, early in the solar system's history, Pluto collided with another large object. The collision wasn't head-on that would have destroyed both bodies. Instead, it was a glancing blow, where the impactor struck Pluto at an angle. The energy released by such a collision would have been immense. Temperatures would have soared to thousands of degrees. Rock and ice would have vaporized, creating a cloud of debris orbiting Pluto. Over time, perhaps thousands or millions of years, this debris coalesced, forming Charon. This scenario is similar to the leading theory for the Moon's formation. About 4.5 billion years ago, a Mars-sized object called Theia collided with the early Earth. The debris from that impact eventually formed the Moon. The similarities between Earth-Moon and Pluto-Charon particularly. The large size of the satellite relative to the primary body suggest that similar processes might have been at work. But there's a key difference: the energy involved. To create Charon through a giant impact, the collision would need to provide enough energy not just to shatter the impactor, but to heat the resulting debris enough to allow differentiation. Remember, the detection of CO suggests Charon underwent differentiation, that its interior separated into a rocky core and an icy mantle. Differentiation requires heat. For Charon to differentiate, its interior would need to reach temperatures where ice becomes soft enough to flow, allowing denser materials to sink. That requires significant energy input. A giant impact provides that energy. The collision itself releases kinetic energy as heat. Additionally, as debris coalesces to form Charon, gravitational potential energy converts to heat, a process called accretional heating. Finally, short-lived radioactive isotopes present in the early solar system, like aluminum-26, would have provided additional heat through radioactive decay. Computer simulations support this scenario. Models show that a glancing impact by an object roughly 400 to 600 kilometers in diameter, striking Pluto at speeds of several kilometers per second, could produce a debris disk with enough mass and angular momentum to form Charon in its observed orbit. Critically, these simulations show that the debris would be hot enough to undergo differentiation. Rocky material would settle into a core, while lighter, icy material would form the mantle. Carbon dioxide, locked in the icy material or created through chemical reactions during the hot, early phase, would be incorporated into this mantle. Over billions of years, Charon would cool. The surface would freeze solid, creating the icy crust we see today. But deep inside, the rocky core would retain heat longer, potentially allowing liquid water to persist in a subsurface ocean for hundreds of millions, perhaps even billions of years. This is the giant impact theory, a violent, energetic origin that set Charon on a path toward differentiation, geological activity, and eventual freezing. But there's another possibility. The second formation theory is the binary capture hypothesis. In this scenario, Pluto and Charon didn't begin as one body. Instead, they formed separately in the early solar system, in the region beyond Neptune, where countless icy bodies were taking shape. Through chance, or perhaps through gravitational interactions in a crowded young solar system, Pluto and this proto-Charon found themselves on intersecting paths. When they collided, the impact was neither too hard nor too soft. If it had been too violent, both bodies would have been destroyed. If it had been too gentle, they would have bounced off each other and continued on separate paths. Instead, the collision was just right, a Goldilocks scenario where the two bodies merged their orbital energy, capturing each other into a mutual orbit. This is called a kiss and capture collision, and it's a rare event. The conditions have to be very specific. The relative velocities must be low, just a few kilometers per second. The angle of approach must allow for enough momentum transfer to bind the two objects without shattering them. But it's not impossible. In the crowded environment of the early Kuiper Belt, where gravitational interactions were common and objects moved in overlapping orbits, such collisions could occur. The binary capture theory offers some advantages. It doesn't require as much energy as a giant impact, which means it doesn't necessarily produce the extreme heating that leads to differentiation. However, it doesn't preclude differentiation either. If proto-Charon formed with enough mass and contained sufficient radioactive isotopes, it could have differentiated on its own, independent of the capture event. Additionally, binary capture can explain the mutual tidal locking we observe today. After capture, tidal forces between Pluto and Charon would have dissipated rotational energy, gradually slowing their spins until both were locked. This process takes time, millions to hundreds of millions of years, but it's inevitable for two closely orbiting bodies. One challenge for the binary capture theory is explaining Charon's size. For capture to work, Proto-Charon would need to be quite large, roughly the size it is today. That raises the question, where did such a large object form? In the early Kuiper Belt, many large bodies were forming. Pluto itself is one of them. Eris, Makemake, Haumea all are dwarf planets comparable in size to Pluto. It's plausible that another large body formed nearby and eventually encountered Pluto in a capture event. But the evidence is less clear-cut than for the giant impact theory. Computer simulations of binary capture show that it's possible, but they also reveal that the resulting orbital configuration often differs from what we observe. Charon's nearly circular orbit and its alignment with Pluto's equator are easier to explain with a giant impact, where debris naturally settles into an equatorial disk. Still, binary capture remains a viable alternative. The detection of carbon dioxide complicates the picture, but it doesn't rule out this scenario. Which brings us to the critical question: what does the new JWST data tell us? The detection of carbon dioxide on Charon's surface is a piece of evidence that favors the giant impact hypothesis, but it doesn't prove it conclusively. Here's why: CO requires differentiation, differentiation requires heat. The giant impact naturally provides that heat through the collision and subsequent accretion. But differentiation can also occur through other heating mechanisms, primarily radioactive decay. If Proto-Charon formed as a large, independent body and contained enough radioactive isotopes, it could have heated internally and differentiated without needing a giant impact. The CO we detect today could have originated in that early differentiation event. However, there's a complication. Differentiation requires not just heat, but enough heat sustained over a long enough period. For a body of Charon's size, radioactive decay alone might not provide sufficient energy. Models suggest that bodies need to be at least 500 to 600 kilometers in diameter to retain enough heat for full differentiation. Charon is 1,212 kilometers, so it's above this threshold, but just barely. A giant impact would have provided additional heat, making differentiation more certain and more complete. This is why many scientists favor the giant impact theory. But there's another line of evidence to consider: Charon's tidal evolution. If Charon formed from a debris disk following a giant impact, its initial orbit would have been much closer to Pluto than it is today. Tidal forces would have gradually pushed Charon outward while slowing both bodies' rotations. This process would have dissipated significant energy as tidal heating, which could have contributed to keeping Charon's interior warm for longer. Binary capture, on the other hand, would produce different tidal evolution dynamics. The timing and extent of tidal heating would depend on the initial orbital parameters after capture, quantities that are hard to constrain. So where does that leave us? The current scientific consensus leans toward the giant impact theory, but it's not definitive. Both scenarios are physically plausible. Both can explain the major features we observe: Charon's size, its orbit, its differentiation, and its surface composition. What we need, what scientists are hoping for, is additional data. Future observations with Webb might detect other compounds that could distinguish between the two theories. Or perhaps a future mission to the Pluto system, equipped with seismometers or ground-penetrating radar, could probe Charon's interior structure and resolve the question. For now, the mystery endures, but we've narrowed the possibilities. And every piece of evidence brings us closer to the truth. But Charon's formation is only one part of the story. There's another question, equally fascinating: did Charon once have a subsurface ocean, and if so, what happened to it? When New Horizons captured images of Charon's surface, one feature stood out: the vast canyon systems that scar the Moon's equatorial region. These canyons, collectively known as the Serenity Chasm System, stretch for hundreds of kilometers. They're not impact craters, they're tectonic fractures created by internal stresses that pulled the surface apart. On Earth, tectonic features like rift valleys form when internal forces cause the crust to stretch and fracture. On Charon, the most likely cause is expansion, specifically the expansion of freezing water. Here's the physics. Water is one of the few substances that expands when it freezes. Most materials contract when they transition from liquid to solid, but water's molecular structure causes it to take up more volume as ice. This is why ice floats on water, and it's why freezing water can crack pipes, split rocks, and fracture planetary crusts. If Charon had a subsurface ocean early in its history, and that ocean gradually froze, the expanding ice would create immense internal pressure. This pressure would fracture the overlying crust, forming the canyon systems we observe. The scale of these fractures suggests the ocean was substantial, perhaps hundreds of kilometers deep. Thermal models support this. If Charon differentiated, the outer mantle would have been primarily water ice with enough heat from formation and radioactive decay to keep a subsurface layer liquid for an extended period. How long that ocean persisted depends on several factors: the initial temperature, the amount of radioactive isotopes present, and the presence of antifreeze compounds like ammonia. Ammonia is critical here. Pure water freezes at 0 degrees Celsius, but ammonia-water mixtures can remain liquid at temperatures as low as -100 degrees Celsius, depending on the ammonia concentration. If Charon's ocean contained even a few percent ammonia, which is likely, given ammonia's abundance in the outer solar system, the ocean could have remained liquid much longer. Some models suggest the ocean could have persisted for 1 billion years or more. Others suggest it might have frozen within a few 100 million years. The uncertainty stems from our incomplete knowledge of Charon's internal composition and initial heat budget, but the evidence for a past ocean is compelling. The fractures, the surface geology, and the thermal models all point in the same direction. Charon was once a world with liquid water beneath its ice. And where there's liquid water, the question inevitably arises: could there have been life? Why did Charon's ocean freeze? The answer comes down to thermodynamics. All bodies in space lose heat over time. For Charon, the primary mechanism is radiative cooling, heat radiating away into space as infrared radiation. In the early solar system, Charon had several heat sources. The most significant was accretional heating, the energy released during Charon's formation. Whether Charon formed through a giant impact or binary capture, the process of material coming together and compressing would have generated substantial heat. Additionally, radioactive decay provided ongoing heat. Isotopes like aluminum-26, which was abundant in the early solar system, decay rapidly, releasing heat in the process. With a half-life of just 717,000 years, aluminum-26 would have been a powerful heat source during Charon's first few million years. Longer-lived isotopes potassium-40, thorium-232, uranium-238 continue to decay today, but they produce far less heat than aluminum-26 did early on. Finally, tidal heating might have contributed. If Charon's orbit was initially more elliptical, tidal flexing from Pluto's gravity would have generated heat through internal friction. However, as the orbit circularized, which happens relatively quickly, tidal heating would have diminished. Over time, these heat sources waned. Accretional heat dissipated, aluminum-26.